Very nice. I mean, well, let's see. Does it work? I'm getting some sound also on the.
Yes, sir. It has started.
Very nice. Wonderful. It's good that one can interact. Very good. How nice. So now our deliberations will all be on packed beds. That's a very large class of fluid flow, fluid solid systems problems, you know. Now, the this is the right time to start looking at it, because where we ended last time, we had already gone beyond single particles. If you remember, in the last class, I said that we have done free settling in great detail, but then I also covered the case of hindered settling, right? So basically, we had a bed of solids and they were settling, and I said that the settling velocity u subscript s for a uniform suspension, that's the assumption we made, for a uniform suspension can be as much as 2 to 5 fold lower, okay, than what we calculated under various hydrodynamic conditions for free settling. Okay, it's very much lower. And now this problem is much more difficult to solve, and there is no analytical type solution like we had for the free settling cases, and we did virtually every case until turbulent flow. So there are a large number of empirical correlations that were developed, and all the correlations depended on a variable that we defined as epsilon, or sometimes also called E, which is the voidage or the void fraction, sometimes called porosity of the system, in the hindered settling. So basically, the equations all take the u subscript t, or the free settling terminal velocity, multiplied by some function, and they can be very complicated functions. I gave you a power law equation, some function of the voidage of the bed. That's also a bed in a way, a bed of solids. And then we raise that in the simplest case, that epsilon or E to the power epsilon to the power n, and ut into epsilon to the power n gave us the settling velocity. So basically we had something like this. So us was the settling velocity for the suspension of particles, for the uniform suspension. Ut was the limit in the free settling case. Epsilon was the void fraction in the uniform suspension, and n was the exponent. And I gave you a mnemonic device, a graph, by which for various flow regimes, this n had been empirically tabulated, found experimentally. So here is the Reynolds number on the x-axis in log again, going again from 0.1 to 10 to the power 3. And the value of n progressively decreases, and that's the appropriate value of n to use in the correlation for the hindered settling velocity. And of course, you have to find the free settling velocity that we have already spent a long time. Very well. So now, even what we did there is in some sense a bed of solids, except that in a normal packed bed, the bed of solids is stationary and we have fluid flow through that bed. While in our hindered settling case, in the gravity at least, the fluid was stationary and the solids was moving at downwards. Normally in the packed bed, the geometry is opposite. We make the flow move upwards and we keep the particles stationary, at least in a packed bed. Of course, we can move the particles. The bed itself we can move, and we have a large number of moving bed configurations, also called fluidized beds, and that we can do after minors. And that's a more interesting case of a fluid bed, of a packed bed, because a large number of reactions, chemical reactions, combustion, and other are carried out in fluidized beds, because the volume in which you can do all things in the interstitial spaces of the particles, between the particles, increases and gives us many more possibilities. Anyway, but the equations that we are going to develop for pressure drop, velocity through a packed bed, they are in some way, the fluidized bed also builds on the same equations. Okay, now what are these equations based on? They are based, all of these operations of flow through packed beds are based on basically a Darcy's type of law. Darcy's equation, I don't know if you encountered it in your fluid mechanical course, fluid mech course before. So all of these are based on Darcy's law, but we have to suitably modify the Darcy's law into more and more complex forms so that we can treat the application that is desired. So in its most elementary form, what does this Darcy's law equation tell us? So as you can see on the screen, Darcy's law is your equation 1. And what it tells us is that if small u is the average velocity of the fluid, okay, such as 1 by a dv by dt or something like that. So it's an average fluid velocity, not necessarily the velocity through the bed, but through a superficial velocity, as if the bed were empty. We will define all of these things over the next couple of classes. So if u is that average velocity of flow, and L is the height of the packed bed or the thickness of that bed, in principle, that L could even, this could even apply to a filtration process. So L would then be the thickness of the deposit of the filter cake, for instance. Okay, so L here would then be, in our case, the thickness of the packed bed. And if delta P is the pressure drop across that bed, mu then is the viscosity of the fluid around in the bed, and u, as I said, we could define as 1 by a dv by dt, where v is the volume of fluid which is flowing in time t, and a is the cross-sectional area of the bed, right? That's how we would define the instantaneous average or average velocity. Okay, so what Darcy's law says is that this average velocity of flow is directly proportional to the pressure drop through that bed. It's inversely proportional to the length of the bed, or in other words, you can say it's proportional to pressure drop per unit length of the bed. Okay, another way of putting the same thing. And it's inversely proportional to the viscosity of the fluid. Okay, and this u is related to delta P upon mu L by the Darcy's law constant, capital K, in equation 1. So you get, in a very simple form of original form of Darcy's law, U is equal to capital K delta P upon mu L, where I have defined all the terms, and here U is 1 by capital A dV by dt, where A is the cross-sectional area, V is the volume of fluid flowing for any time instant. But you see, this Darcy's law is a very, very simple form. Of course, we can do certain things even with this simple form, but none of the characteristics of the bed, for instance, the void fraction epsilon, or I have called the void fraction E in the subsequent equations. Both terminology, both symbols are used to denote void fraction. So nowhere is that coming into account, and a packed bed, if we do not have the void fraction, then pretty much the equation is not complete, you see. But even this simple equation, though I don't know if you have done it before, but it has some echoes of previous equations that you would have done at least in the transport phenomena course. That is given by equation 2, which is our laminar flow equation for a mean velocity of a fluid flowing in a circular pipe. This Bird-Stewart Lightfoot has derived this in one of the early chapters, maybe chapter 3 if I remember. So what that equation told us is that there was a linear relationship, this equation 2. So there was a linear relationship between the rate of flow and the pressure difference. And in general, that derivation in Bird-Stewart Lightfoot's transport phenomena book was for streamlined flow. Okay, it is not a generalized relationship valid for all flow regimes, but it was for streamlined flow. So this is expected in a way because Reynolds number for the flow through the spaces through the interstices in any granular packed bed or any flow is normally low. Low meaning it could be of the order of 100, below 100. And since both the velocity of the fluid and the channels in the bed are fairly small, this will work for the streamline flow, and you can compare it with expression in the circular pipe, which is equation 2, where left hand side is u1, which is the mean velocity of the fluid through the pipe. D1 is the diameter of the pipe. Capital L is the length of the pipe. And the famous Hagen constant of 32 comes in the denominator. So you get U1 is equal to D1 squared delta P upon 32 mu L. Right? This is the well-known equation that you had derived. And if you see equation 1 that Darcy found by experimentation, it has a form that is somewhat like the expression for the fluid flowing through a circular pipe. Now, suppose, how do I modify equation 2 for our purposes? I mean, because here again voidage doesn't appear, right? Even in that it was a free flow through channels or circular pipes and etc. But suppose you were to assume, if you were to assume that your free interstitial spaces in the packed bed, now in the packed bed, consists of a large number of channels, then in some way we can adapt the same equation 2 for our purposes. But now the constant 32 that appeared in the denominator is not 32, but something else that has to be determined experimentally. and D some equivalent diameter for the spaces, pore spaces that are there in such a bed. So in other words, you can write this equation, you can modify equation 2 and you can write it as shown in the slide, which is equation 3. So this equation reads U1 is equal to dm squared delta P upon K prime mu L. So the dm now is some equivalent diameter of the pore spaces and the K prime is some dimensionless constant, which is not 32 because the 32 was for a structureless fluid. I mean, there was no particulate matter in that circular pipe. So K prime is some constant, dimensionless value, dimensionless constant whose value is dependent on the bed structure, on the structure of the bed, or how the pores are, and etc. And that has to be found. Of course, this is not, I'm not saying this is a wonderful treatment because it is not strictly speaking rigorous, because these channels are not, they are not really individual channels which are disconnected from each other, but they are all part of an interconnected series of passages in the packed bed, right? So all of those interconnections are not included in equation 3. Okay, but the interesting thing is that we can adopt the same form that Darcy and Hagen and others adopted for the flow through the circular pipe. Okay. So now, as I said, very important property of the packed bed and is the porosity or the voidage, which is we are going to call by symbol E or epsilon. According to me, and as you saw also in the hindered settling case, this is a very important parameter, and we have to find a way to incorporate it in the equations. You understand? What I mean is, this parameter has a huge effect, a large effect on the resistance to the flow of fluid. Okay, it has a very large effect on the resistance to fluid flow. And we define this E voidage coefficient as the proportion of the total volume of the bed, which is accounted for by the free space between the particles. Okay, so the void space divided by the total space. Okay, because we have an excluded volume effect here. Fluid can't go through those particles, they are not porous, and those constitute the excluded volume. And depending on how tightly the bed is also compressed, we will have different E values for different beds, which will change the resistance to flow. In other words, if you have a very loose packing, then the resistance to the flow will be lower. Now, can we take, now you see this void fraction, can we take it to be approximately constant for the bed? For the moment, we are going to do that. We are assuming that the particles are all randomly distributed, particles are all packed randomly, and that this void fraction E is approximately constant throughout the packed bed. In other words, we are not modeling any anisotropic or direction dependent effects. We are saying the resistance to flow is the same in every, is uniform, is the same in every direction. Okay. Now, in such a bed of uniformly or randomly distributed particles with void edge E, the average free cross-sectional area is E times the total cross-sectional area. All right. So what we can do is we can write the average velocity, which is measured over the whole cross-sectional area, right? That is how the original Darcy's form, or also called the superficial velocity, is like a reference. What we mean is, suppose we emptied the whole packed bed of solids, and we emptied it out of solids, and then what is the, we know the cross-sectional area, we measure the flow rate, and then we divide the two, and that gives us small u in equation 4. So that is a measure of the average velocity or the superficial velocity or the average superficial velocity. Various terms are used. So that's essentially measured over the entire cross-sectional area of the bed. However, generally we are more interested in the average velocity through those empty or interstitial spaces of the packed bed, or the capillary spaces in the bed, and that velocity we called as u1, okay, in the previous equation. So u was the average or superficial velocity, and u1 was the average velocity in the capillaries constituting the packed bed. And basically both of these velocities are related by linearly by the void edge, so that u is u1 times the void edge E, and that is our equation 4. Okay. So what we can do is, so what is this equation telling us? It's saying that the velocity in the average velocity in the capillary spaces times the void edge is our superficial velocity, which was what Darcy originally worked with. So we can take the u that is there in the Darcy and the Hagen type circular pipe expressions, which we modified in equation 3, and we can substitute equation 4 in this, and that gives us the equation 5, which is somewhat better. So what that equation tells us is u by E is equal to all the terms on the right hand side, which remain the same, dm squared delta p upon k prime mu into L. Okay. Now this equivalent diameter, we have already done a lot of thing on it. We said you only said that you can call it. It can be a hydraulic diameter, etc. I mean, and then I said, well, if that's not shape independent, I mean, etc. And we did quite a lot of things. But basically, for a streamlined flow, this dm prime depends on the volume of the voids, and it also depends on the surface area of the packed bed, or rather the material that is forming the packed bed. Surface area of the material, total surface of the material that is constituting the bed. So can you, for now, think of a simple expression for this dm prime on the right hand side, which is related to the void fraction of the bed and also dependent on the volume and surface of the bed. Is my question understood? What I said is that this d prime m can be related to the bed properties, that is the volume, surface, porosity. So till now we didn't have to do this, but for packed bed we have to think on how dm varies with epsilon or E, how it is related to the specific surface area of the material by which I mean the surface per unit volume. So can anyone try and come up with an expression? After all, it is a geometrical thing, concept. Okay, I will give a hint. Let us first do that thing in words, and then let us see if the class can later put it in the form of symbols. I hope you can see the next slide. Yeah. So, without any loss of generality, this dm prime can be written as the volume of the voids, that's the numerator of the expression on the slide, divided through by the total surface of the material of the bed, that is the particles. If you were to find out the total surface area, add them all up for each of the particles, whatever be their shape, you can always find the total surface, and divide through by that number the volume on the voids. That is the measure of dm prime. So now suppose you were to take a bed of unit volume. What will be the pore space? Can you fill in symbols in terms of the parameters that were there in the previous equations 1 to 5? What is the pore space? How much since you know the voidage, what is the pore space and what is the exposed surface area of the particles? This you should be able to find. And once we can find both the numerator and denominator and express them as functions of the voidage, then we have a much better expression which captures the essence of the packed bed, and that is called Kozeni's equation. It was derived by Kozeny. It's given some other names also of, in the literature, but we are going to call it Kozeni's equation. So, but before we do that, you have to take the slide that is on your screen, which gives you the meaning of dm prime in words and as a ratio. You have to now put symbols to that, and of course the voidage will be there in both the numerator and the denominator of this equation. So I just want that the class thinks on this and tries to come up with this. If there is one volume of the bed, pore space is epsilon. So that's your numerator. So now what is the denominator? उस पर आप सोचिए जरा. Any suggestions? If we take unit volume, then you can define a surface area per unit volume for the bed, right, of the material, so, which is called generally called specific surface area, small s or many times capital S. So capital S is the surface of the bed per unit volume. So for that unit volume, the pore space is E. So the numerator in this expression is E. This ratio is E. But what will be the denominator in terms of E and the specific surface area? Definitely, it will be 1 minus E into the specific surface area, capital S, where specific surface area is surface per unit volume. So your d prime m can be written as E upon 1 minus E into S. So that should be the next equation. Yes, that is equation 6 appearing now on your screen. S is the specific surface area in meters squared per meter cubed of the material, specific surface of the material in the bed. And now, once you know this equation, why not substitute it into the equation that you obtained for U by E and find out what you get. In other words, solve for U. You had an expression for the superficial velocity. You related U1 to U, so you substituted for U1, you substituted U by E, and now I suggest you put all of this into, so dm prime rather, you can now use the equation 6 and substitute it into the previous equation and tell me what you find. And whatever you find is Kozeni's equation. So if you were to substitute this, if you put this into equation 5, you will get what is on the screen. In other words, the superficial or average velocity, superficial velocity is proportional to delta P by L, of course. Of course, it's inversely proportional to small mu, as Darcy said, but it's also inversely proportional to square of the specific surface area of the bed. It's directly proportional to the cube of the voidage. It's inversely proportional to 1 minus E to the power squared. And all of this is now, and then there's the Darcy's constant K prime. And now the Darcy's constant, whatever you find, is an act, and that's what Kozeny did a lot of experiments, and he suggested that when you represent the equation in this way, equation 7, Kozeny's equation, then K prime is a constant. And he did a number of experiments to determine the value of this constant for packed beds containing solid spherical particles. Okay, that's called Kozeny's constant K prime, and that is a value of 5. Okay, so Kozeny's equation then becomes U is equal to 1 by 5 into E cubed upon 1 minus E whole squared into delta P by L divided by 1 by, within brackets, mu into S squared bracket closed. That is equation 7, and that's Kozeny's equation for the packed bed. Okay, now strictly speaking, even this is not 100% valid, and it has been later research has shown that K prime is not a true constant. K prime is in fact a function of particle shape, for instance. But all of Kozeny's experiments were done on spherical particles, and he didn't have to worry about the orientation of the particles or the shape, etc. So K prime is somewhat much more complex, but for the moment, let us take the Kozeny's constant value of 5, and we write equation 7 as Kozeny's equation, and this is a reasonably good starting point for our further discussion on packed beds. Okay, so let me summarize what we have done. We spent quite a lot of time on the free settling case, and we kind of did it as well as we could. It could have been done, I think, and went all the way to 10 to the power 5 Reynolds number. And for different shapes and any shape independence also. But then we said that in a bed of Setelius, that UT is it's very much over approximation, and we gave some correlation, empirical correlation for the bed of solids, which was settling. But we said that in the packed bed where the geometry is inverted and the flow is generally from bottom to up and the bed is stationary, we have to start from a form of Darcy's law and then keep modifying the Darcy's law to pick the important characteristics of the flow in the presence of those solids and how it essentially that flow velocity, average flow velocity, depends on the void fraction of the packed bed. Of course, it also depends on all the other Darcy's variable, delta P per unit length of the packed bed, and also inversely depends on viscosity and on square of the specific surface area. So this is Kozeni's important contribution to flow through packed beds. Okay, and we will continue from here. Okay, and we will see how to calculate these pressure drops, which are very important for all reactors and heterogeneous catalysis, etc. All right, any questions? Okay, so this recording then is anyway available to everybody. They can follow it, and there are some very, I mean, Coulson Richardson, then Faust's book. All of them treat this, but they all treat them in different ways. And sometimes this Kozeni's equation forms are given. Sometimes Karman-Kozeny, which is we will do that later. It's a more approximate equation, but very widely used. And sometimes the equations are also called as variants of Ergun's equation. So you will find different things. It depends what material on the net you will consult, but it's fine. What we have done is fairly is a good starting point for our further deliberations. Okay, thank you very much. Enjoy, and we will continue.